Good morning. Our last lecture. Okay, we're going to finish up simple harmonic motion. As soon as I'll get yesterday and today both videos posted at the same time. All right, we were talking yesterday about the fact that we had anytime the restoring force is proportional to the distance. So with our spring, when that object is at its equilibrium position, there's no force on it. If we pull it out this way a little bit, then there's a force on it back toward the equilibrium position. If we moved it this way a little bit, there's a force this way toward the equilibrium position. The force wants it to go back towards the equilibrium position. If that force is proportional to the displacement, then we have simple harmonic motion. And that's because we get this type of equation. We get so the force is proportional to x. And we get the second derivative of x is equal to something times the same function. Again, this is very easy to solve. Sine or cosine function works really nicely. Anytime the force is proportional to the displacement. Springs, the force is proportional to the displacement. That's an easy one, right? What about other things? There are other things. We'll talk a little bit about a simple pendulum. A simple pendulum, all the mass is at the end. The string is massless. All the mass is at the end. That's a simple pendulum. A physical pendulum is like a long rod that's rotating back and forth. This would be a physical pendulum, right? The mass is uniformly distributed up and down the length here. It's not all at the end. So you have to take that into account. It's a little more complicated, not impossible, but we don't have time to deal with that. So we'll just deal with simple pendulum. If we draw out a simple pendulum, let's see what our free body diagram looks like. We've got tension. We've got gravity. I'm just going to put a dashed line here. Excuse me, dashed line here, because we want to split that up into the right coordinate system. What's the coordinate system we want to use? Well, we like to pick the direction of the acceleration. I would pick this direction here, tangential and radial as my coordinate system. So I'll break up the weight of gravity into mg cos theta and mg sine theta. This is theta, right? Now we say sum of the forces equals ma. What's the force causing this thing to go back into its equilibrium position? It's the force of gravity, right? Mg sine theta. Now we make a small angle approximation. If theta is small, the sine theta is approximately equal to theta in radians. So we get minus g theta is equal to A. A is the second derivative of our distance, our arc length, and arc length is our theta, right? So what do we get for our equation? Minus g theta is the second derivative where this is the length of that, right? The length of the string. Okay, so if we make a small angle approximation, we get this relationship. We can say, oh, this is an easy one. Theta is something times cosine omega t plus phi. What is omega in this case? It's not k over L. There's no spring constant, right? The mass canceled out of our equation. What is it equal to? It equals the square root of g over L. So the frequency of a pendulum does not depend on the mass. This is a simple pendulum, right? Does not depend on the mass. It depends on gravity and the length. Most of what we talk about is undamped oscillation. So, for example, a mass here moving up and down. Maybe it started here when we let go of it. Something like that, right? Undamped. There's no friction, no air resistance. As this thing oscillates, it always goes back to the same amplitude. It will oscillate back and forth like that forever. But in the real world, we know that there's usually a little friction or air resistance. This is called a damped oscillator. Damped oscillations. One way to visualize that's really damped, right? So as this thing goes up and down, It starts here, but it goes only to here, and then it goes only to here, and then it goes only to here, right? So there's sort of this this window that's closing on it, and each time it oscillates back and forth, the amplitude gets a little bit smaller. Damped oscillations. This, what I've drawn here, is what's called underdamped. We could also make the damping much greater. So you see how this one passes through its equilibrium position multiple times, underdamped. Let's say, yeah, the thickness of the fluid affects the damping. Yeah, so if it was just air, it would oscillate quite a bit, right? It would only lose a little bit each time, right? A little bit each time. If I put it in water, it would lose a lot more each time, right? On each oscillation. If I put it in something thick oil or something, it would slow down even more, lose that energy even faster. Let's picture a door. You have a door that can swing back and forth, and you open it to walk through, and you let go, and you don't want the door to stay there. So you put some kind of a spring on it to pull it back towards its equilibrium position. But what if you have an underdamped situation, the spring pulls it back and it passes right through its equilibrium position and swings in the other direction. And then it swings back, and eventually it stops. It's a little bit less each time, and eventually it stops at the closed position again. That's underdamped. If it's like a normal door that has a jam on it, and the door would slam into that door jam, and it would be a real loud thump when it hits the door jam. You might not want that. You might want the door to close slowly and not slam when it gets to the closed position. So we have something, we could have this situation, right? It starts out, let's start it out at some maximum displacement. And then over time, you could have it close super, super slowly so it doesn't slam, but it might take forever for the door to close. This is overdamped. Okay, so the door isn't gonna slam, but it might take 2 hours to close. You've got it set so it just very, very slowly closes. What you want is what we call critically damped. Damping means that you're dissipating the energy somehow. If you're not dissipating the energy in that oscillator, it oscillates back and forth forever with the same energy. It makes it to the same amplitude, back to the same amplitude each time, because you're not dissipating the energy. If you're dissipating the energy through friction, air resistance, something like that, then the amplitude becomes less and less and less each time. You're taking the energy out. So you've seen on the tops of doors, they have these pistons in there that will pull the door closed, but then there's some kind of an air piston that causes it to close slowly. It damps the motion, but you don't want it over damp because it'll take forever for the door to close. You want the door to close as quickly as possible without passing through its equilibrium position, without slamming. That's critically damped. So it starts and it goes as quickly as possible without passing through equilibrium. Shortest time without crossing the axis. So that's damped. And then I think we mentioned we could have driven oscillations also, where we add energy. So somehow we're adding, like pushing a kid on a swing, right? You give them a push, you added a little energy, you come back, you give them another push, you add a little more energy, right? Something like that, right? You're lifting that spring up and down, up and down, up and down, adding energy. And if you're adding that energy at just the right interval, just the right frequency, then it does something like this, right? Driven oscillations. Okay, let's take a look at this. Can't play it.
The Olympic Peninsula, extending northward from the lower end of Puget Sound for a distance of more than 90 miles, is separated from the mainland throughout its length by the waters of the Sound. At its narrowest point, Tacoma Narrows, the width of the Sound is 4,600 feet. In 1937, the state of Washington created a toll bridge authority, which was empowered to construct bridges within the state. By June 1938, an amount of $6,400,000 to build the bridge across Tacoma Narrows was secured, 9 feet apart, and by stiffening I-beam girders 8 feet tall. Each of the two main cables is made up of many strands of iron wire. The cables terminate at each end of the bridge in concrete anchorages. After the Tacoma Narrows Bridge was open to traffic, its unusual behavior was noted by a number of motorists. This behavior was described by an engineer associated with the bridge project.
Immediately after the bridge was put into service, many motorists who crossed it commented on the extraordinary oscillations of the roadway. These oscillations, or waves, were sufficient to cause discomfort to occupants of cars, and some motorists made long detours to avoid recrossing the bridge. The oscillations were in a vertical direction, some having up and down motion as large as 5 feet. The amount of up and down motion did not seem to depend on the wind speed. It seemed wise to us to make a systematic series of observations of the oscillations of the bridge. We observed, first, motions of considerable magnitude with wind velocities as low as 3 or 4 miles per hour. And second, the violence of motion was not proportional to the velocity of wind.
On November 7, 1940, at 5 a.m., Mr. Kenneth Arkin, chairman, Washington Toll Bridge Authority, was awakened by the wind.
I got up and drove to the Narrows Bridge to check it. I went to midspan and measured the velocity of the wind to be 38 miles per hour. The bridge bounce was noticeable, but of no great magnitude. Hurrying back to the observation house, I encountered Mr. Farquharson, our consulting engineer.
While Ken Arkin was at the observation house, I went to a position on the axis of the bridge to photograph its motion.
That bridge is
Suddenly, a
big
motion
steel,
of catastrophic
8-foot
proportions
tall steel
developed.
I-beam.
As quickly as
not
possible,
rubber.
I reached a station just outside the tower to photograph the motion of the bridge. It was quite impossible to operate a camera on the main span, so violent was its motion.
I had climbed to the observation house and looked through the transit. Suddenly, the midspan disappeared from my vision. The midspan seemed to have blown north approximately half the roadway width, coming back into position with a twisting motion. I yelled to have the traffic across the bridge stopped. Turning back to the transit, I noticed the twisting motion had increased to great proportions. I could not keep the light poles in my line of vision long enough to determine their exact motions. I then saw a car parked beyond the tower on the right side of the roadway. I noticed it suddenly careened to the left side of the road. The driver fell out, grabbed the curb, and hung on for what appeared to be several minutes. The bridge calmed down sufficiently for him to struggle in.
As a reporter on the Tacoma News-Tribune staff, I had gone to watch the bridge. I drove onto the bridge and started across. In the car with me was my daughter's Cocker Spaniel, Tubby. Not until I reached the first towers did I realize that something was terribly wrong. Just as I drove past the towers, the bridge began to sway violently from side to side. The tilt from side to side became so violent that I lost control of the car. I jammed on the brakes and got out of the car, only to be thrown onto my face against the curb. Around me, I could hear concrete cracking. I started back to the car to get the dog, but I was thrown before I could reach it. The car itself began to slide from side to side on the roadway. I decided the bridge was breaking up. My only hope was to get back to shore. I crawled 500 yards or more to the towers. My knees were raw and bruised. My hands were swollen from gripping the concrete curb. But I was spurred on by the thought that if I could reach the towers, I would be safe.
I made an effort during a momentary decrease in the violence of the bridge motion to reach the car, but the car began to shift about in a most alarming manner. While I was out on this portion of the span, I took the opportunity to examine the state of the bridge. As far as the eye and ear could detect, the oscillations were causing no distress in the girder. Then, as I was sighting along the outside edge of the bridge, I saw a distinct break in the steel I-beam. From this point on, failure occurred so rapidly that observation was difficult and impression and fact are somewhat mixed. A whole section fell out of the bridge. After this first section fell, the whole bridge, almost at once, ceased its violent twisting motion and fell into a much easier vertical motion. The failure became progressive along the main span, the shock of each successive unloading of the main span producing a corresponding shock in the side span from which I was attempting to make observations. 2 of these shocks were of sufficient force as to throw me violently to the deck.
Those who stood on the shore and watched the bridge in its death agony still can have no conception of the violence of movement felt by one out beyond the towers. Safely back at the toll plaza, I saw the bridge in its final collapse and saw my car plunge into the Narrows. With real tragedy, disaster, and blasted dreams all around me, I believe that right at this minute what appalls me most is that within a few hours I must tell my daughter that her dog is dead when I might have saved him.
Okay, he's a little melodramatic, but you get the point. So the idea there, driven oscillations, right? The speed of the wind wasn't so important. What was important was it hit that just the right frequency. It was causing just the right disturbance, and it stayed steady at just that right rate. I am told that for this same reason, soldiers don't march over bridges. Soldiers, when they march, right, their feet all come down in unison. Boom, 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 boom. And if the pattern of their feet hitting the ground happened to match the natural frequency of the bridge, it might get oscillations going in the bridge. So they don't march, they walk over the bridge. That means everybody's feet are coming down at different times, and you don't get that same buildup of driven oscillations going. So that's the idea here. Driven oscillations in the bridge. It was the wind blowing at not so much a great speed, but just the right speed that it stimulated the natural frequency. It excited the natural frequency that the bridge wanted to oscillate at, and got it going. Yeah, so they actually, I saw that they made a replica of this bridge at the University of Washington and put it in a wind tunnel, and got the they got it to repeat the same behavior. And so you do tests, you do wind tunnel tests and things like that nowadays to make sure things like that don't happen. And it's not that it never happens. I believe there was a bridge built for one of the Olympics in London that had similar behavior when people walked on it, the Millennial Bridge or something like that in London. They had one. They had some issues there. I don't know if they went back and retrofitted it with some extra supports or something to take that out, to change the resonant frequency of the bridge. But this is the kind of thing, everything has a frequency it wants to oscillate at. And if you play a musical instrument, well, nowadays you probably have an electronic tuner for it, but in the old days you would use a tuning fork, and you have a small tuning fork, and they have small tines on a tuning fork, have very low rotational inertia, so they vibrate very quickly and make a high frequency sound. And longer tines on a tuning fork have more rotational inertia, they vibrate slowly and make a lower frequency sound. So each tuning fork is designed so that it makes a certain frequency. It has its special resonant frequency, a frequency it wants to oscillate at. A kid sitting on a swing, the length of that swing determines the resonant frequency. What interval do you want to push to drive it and get the oscillations bigger and bigger and bigger? One example I like to use is if somebody drops something in the other room, oftentimes you can tell what it is. You can tell whether it's plastic or metal. You can tell the shape. If it was a glass or a dish or a fork, right? Because everything has a certain resonant frequency and makes certain sounds. You can tell if it's long and thin, like a ruler, or whether it's a big chunk of wood chunk, or whether it's long and thin. You could tell differences because they're gonna vibrate differently and give off different sound. Yeah, it's the same thing. Breaking a glass with sound is the same thing. Mythbusters did a big episode on breaking glass with sound. But if you get the frequency of the sound, you dial in, and it has to be just right. You can take a glass and flick it with your finger and use a microphone and record the signal and see what frequency is the greatest. What frequency does the glass produce when you vibrate it? And then you say, oh, that's the resonant frequency. I'm going to play that exact frequency, and the glass will start to vibrate. In fact, I can show you that. So here's a glass, wine glass with a speaker. There's a speaker right next to it. And look at that. That wine glass is glass, right? It's not rubber. It's amazing how flexible the glass actually is. But as soon as you get it just beyond that point there where it's flexing back and forth, it breaks. So it's the same thing. The sound waves, the air molecules are pushing on that glass, pushing on it just ever so slightly, but if they're all pushing at just the right interval, then the amplitude of that oscillation starts to get bigger and bigger, just like pushing someone on a swing. But if your push is a little off the natural frequency, if it doesn't match the natural frequency, then you don't get that. Sometimes you push and it makes the amplitude bigger. Sometimes you push and it stops it, and you don't get that same buildup. It has to be just the right frequency. Okay, let's let's do a problem. All right, we've got a mass on a spring, frictionless surface, and as it's passing through the equilibrium position with its maximum speed, as it's passing through the equilibrium position with its maximum speed, another mass, clay, a clay ball, plops down and sticks to the top of it. Okay, so this is prior to the collision. So the first thing we want to do is find V max prior to the collision. And then we want to find all the values after the collision. Find A, omega. I guess once we have those, we can have everything else, right? Okay, so let's do that. What is omega? Question about damped oscillations. I don't think so. Period stays the same. All right, so for this one, what do we have? We've got 100 over 4. So this tells us we can figure out how many cycles it makes per second from this, right? And our amplitude, what's our amplitude? Sorry, what's our Vmax? How can you find that? Using omega A. How do we get that? From energy, right? From energy. So 1/2 Ka squared has to equal 1/2 m Vmax squared. So Vmax is the square root of K over m times A, which is omega times A. And what do we get? We get 5 times 2, 10. Is that right? Now we want to know after the collision. What's going on after the collision? It's a collision. So let's use momentum to figure out the speed after the collision. And all we care about here is the x direction. Because in the y direction, what happens? The Earth gets in the way, right? The Earth gets in the way, and that messes us up. The Earth has infinite mass as far as we're concerned, so our momentum conservation doesn't work there. But in the x direction, which there's a frictionless surface, everything's free to move, we can use momentum conservation. And at the end, they stick together. So we get a ratio of the masses, right? V final is m1 over the total mass times whatever the initial, I think it turns out to be 4. It slows down quite a bit. It was moving 10 meters per second. Now it's moving 4 meters per second. So we know our new Vmax. Our mass is now 10. These two objects are, oh wait, what did I tell you what M2 was? Yeah, 6 plus 4 is 10. And then we can find the amplitude. The new amplitude we can get from energy conservation. K has not changed. It's not as much. We dissipated some energy during that collision when they stuck together. We lost some of our mechanical energy, and the amplitude is less now. Oh. There, is that better? Yeah, you could do that too. You can use the formulas. But this, if you forget, you know, I don't use this all the time. I forget those formulas, but energy conservation is, I never forget that, right? I can always use that to figure out what is A in terms of V max and K and M, right? It's very quickly, a couple of lines, I can figure it out using energy conservation. Okay, I've got one more video I wanted to show you, another Veritasium video. It's very good. Since we're finishing up our circular motion chapter recently. Okay, let's take a look at this. This is about the Coriolis force and circular motion and why water swirls one direction when it goes down the drain in the northern hemisphere and the other direction in the southern hemisphere.
Hey, it's me, Destin. Welcome back to Smarter Every Day. Here's the deal. I've created a video in the Northern Hemisphere, and Derek from Veritasium has created one in the South. You have to synchronize these two videos in order for this to make any sense, but it's totally worth it if you do. So click the first link in the video description, get the video ready, and then synchronize on my mark. You ready? 5, 4, 3, 2.
Today, we're trying something that's never been done before. I've made this video, and Destin has made a video on Smarter Every Day, and we want you to play them both at the same time. So there's a link to his video down in the description. Find a way to load both of these videos and then synchronize them on my mark. In 5, 4, 3, 2, 1. We go. In Sydney, Australia, we are at 34 degrees south latitude, which is the opposite side of the world from Huntsville, Alabama. So, which way did the toilets flush? That is the question.
Here in Huntsville, Alabama, we're at 34 degrees north latitude.
And we're going to find out if the water swirls the opposite way here to how it does in the southern hemisphere.
We're making the definitive video to settle this once and for all. It's never been done on the internet. You're going to learn something.
The Simpsons did a whole episode based on toilets flushing the opposite direction in Australia. Plus, other shows have supposedly demonstrated this effect.
So I have seen documentaries that seem to indicate that which hemisphere you're in determines which way the water is going to swirl. But there's this other group of people, and they seem really confident that it doesn't matter where you're at, the water's going to swirl however it wants.
So is this a real effect or not?
The application of this principle to draining water in Earth's two hemispheres is just bunk.
But have you ever just looked for yourself and figured out which way your toilet swirls?
If you try it yourself, you'll find inconsistent results.
Here in Alabama, I've noticed that some turn counterclockwise and some go clockwise.
This sink sometimes drains one way and sometimes the other way.
You see, most toilets have little jets in it, so the swirl direction is determined by the design of the toilet and not which hemisphere you're in.
In any container of water, there's always going to be some rotation. The water is not perfectly still. And it is this, rather than the hemisphere, that determines which way the water will swirl down the drain.
So it's a myth. Crossing the equator does not mean the toilet's going to change directions. But what if we come into the garage and do a more controlled experiment?
But what if we could eliminate all motion from the water?
This is a 1.5 meter kiddie pool.
I have here a 5-foot wide kiddie pool.
Instead of filling the pool with no vorticity at all, I'm going against the way it's supposed to drain. So I'm trying to fill it with the flow going clockwise.
I actually filled the pool in the anti-clockwise direction to be sure that any clockwise motion we see is not due to the way I filled the pool.
So let's let the water settle for a complete day so that we know that it's perfectly still.
And I've left this water sitting here for 24 hours. So it seems like I've damped all of the motions from the filling.
Well, I'm not going to reach in and pull a plug out because that would induce some vorticity. I'm going to use this valve that I have connected to the bottom of the pool.
I really hope this works. Destin, wish me luck.
Good luck. plug, Derek.
I'm about to pull the plug.
Okay, opening the valve in 3, 2, 1. Water should be flowing.
And the pool is draining. But you can't see any motion of the water just yet.
Okay, water's been flowing for a couple of minutes, and I haven't seen anything yet, so we're going to put some dye in it.
To help us see where the water's flowing, I'm going to put some food coloring in on the 4 cardinal directions around the pool.
Check it out, it's like a tornado, like right off the bat. We got a counterclockwise rotation. We filled it up clockwise, and now it's going counterclockwise.
You can clearly see that the water is flowing clockwise in this direction, and that makes sense because that's how it should flow in the southern hemisphere due to the Earth's rotation.
We have a kiddie pool in my garage, and the whole Earth is rotating, and the water's going counterclockwise because I'm in the northern hemisphere. It's real. This is real.
But you can see what a tiny little effect it is, and what extraordinary lengths I had to go to see this effect. So really, you're not going to see it in a bathtub, and you're not going to see it in a sink or in a toilet, because there are other sources of angular momentum that totally wash out this effect.
We just proved it because we just eliminated variables. The Coriolis effect is real.
Have it. It works. To understand how it works, imagine a pool with one edge touching the South Pole.
Think about a pool near the North Pole.
The pool is stationary relative to Earth, but every day it's actually completing one full revolution.
The Earth is spinning on its axis, so the pool spins around the pole once a day.
Now you can see the side of the pool furthest from the pole travels much farther every day than the side right next to the pole.
The whole pool is moving, but the part that's closest to the equator has more momentum, and the part that's closest to the pole has less.
So the outer side of the pool is moving fastest towards the east, and as you get closer to the pole, the velocity decreases down to 0.
Think about these velocities relative to the drain in the middle.
Now imagine we drain the pool.
When we pull the plug, all the water starts moving towards the middle.
Water from the far side is moving too fast relative to the drain, and so it gets out ahead, whereas water from near the pole is going too slow, and so it lags behind.
The side nearest the equator is going faster, so that water outruns the drain. But the water nearest the pole is going slower, so it falls behind. So when the water approaches the drain, it swirls counterclockwise. This is the reason hurricanes swirl counterclockwise in the northern hemisphere.
And this is the reason cyclones swirl clockwise in the southern hemisphere.
The center of the hurricane has lower pressure, just like a drain, so the hurricane swirls just like our pool.
The higher pressure air rushes into the eye of the storm, and just like in our pool, swirls in the direction dictated by the hemisphere.
And that's the truth about toilet swirl.
That was awesome. What'd you think? I definitely learned something. And if you did too, then you should share these videos with your friends.
It's the first internet experiment from 2 different locations. Pretty cool stuff.
So you should subscribe to this guy.
No.
Subscribe to Destin.
Subscribe to Derek. I'm going to actually go to his channel and make sure that you end up over there. Let's.
Okay, both of their channels are good. Smarter Every Day and Veritasium. Very good. If you haven't checked them out, worthwhile. Okay, we good with this? What about if you're on the equator? Oh man. Then it comes down to other factors probably. What else? What other little disturbances are local that would cause the water to start moving in one direction versus the other? So the idea there is that you have speed because of as you move out towards the equator, your speed is actually getting faster and faster, right? Your speed is omega times r. Your r is getting bigger. The distance to the axis of the Earth is getting bigger. And so as you move in, if you have that same speed as you're moving in, like the air does in a tornado or the water does in a tub, as you're moving in towards the center, the one moving faster out distances the drain, and the one moving slower lags behind, and then you get that swirl. Okay. So we finished up 2 chapters this week since the last exam, gravitation and oscillations. there's not a huge amount in either of those chapters, especially gravitation. That's a pretty short chapter, but take a look at it. Don't ignore those. Those will probably be weighted a little heavier on the final than the other material, but the final is cumulative. And no review today. There's a campus function this afternoon, so that I'm going to be attending. So no review today, but I'll send out an email. We'll have plenty of chances to go over material before the final. All right. Enjoy the rest of your day. No more practice exams.